we were just looking at the conservation of momentum that says that the momentum in a system will remain unchanged unless force acts on it. So let's look at what happens when things collide together using the conservation of momentum. So what we have here is whenever objects collide in the absence of external forces, the net momentum of the objects before the collision equals the net momentum of the objects after the collision. So here's a great photograph of two World War I planes colliding in midair. It's an amazing photo. But what I just said was that when two objects collide, you have to look at the net momentum of all the objects before the collision, and then you have to look at the momentum of the objects after the collision. And if you add up all the momentums before, it should equal all the momentums after the collision. Now, a billiard ball, if it hits another billiard ball that is at rest, the first one should stop completely, and the second one will move away with a velocity equal to the velocity of the first ball. The momentum is completely transferred from the first ball to the second ball. And when objects perform a collision like that, we call it an elastic collision. The object isn't the shape of the object isn't changed, it isn't deformed, and heat isn't generated. And if they bounce perfectly, then you have a perfect elastic collision. And once again, the sum of the momentum vectors is the same before and after each of the collisions. So let's look at this in a diagram with the balls. You can see the moving ball strikes the second ball during the collision, and it's going to transfer the red ball is going to transfer all its momentum to the still white ball, and the white ball is going to move away with the same velocity. You can see the velocity here and the velocity here should be the same. Now let's look at two balls moving towards each other and colliding, and you can see the velocities before and the velocities after are equal, but they're opposite. So the momentum is conserved the momentum is conserved during the collision. They both should move away from each other at the same speed. And then if you have two balls colliding into each other and they're moving in the same direction, and a faster ball overtakes a slower ball, it's going to transfer momentum to that second ball, and the second ball then is going to pick up in speed from after the collision. Once again, all these collisions, the momentum is conserved completely, and there's no loss of anything to heat or to deformation of the object. Now, with an inelastic collision, things can become distorted and heat can be generated during the collision, such as like a car crash. You can see that the cars are actually going to change shape. But momentum conservation even holds true in that case. And when they become tangled or coupled together, then we have what a totally inelastic collision occurs, and this is very different. The two objects are now stuck together. As a result of this collision, if you look, we have a moving car here. It hits a still car there, and as a result, the momentum then is shared. Now, this one's moving at 4 meters per second. This one's moving at 0 meters per second, and afterwards, the blue car is going to slow down and give some of its momentum to the orange car, which then is going to speed up. And if you look at and this should occur if they're both of equal mass. And here's the math for it right here. We would say the net momentum before equals the net momentum after. We can substitute mass times velocity for the word momentum, and we can start putting numbers in. Here's the momentum before, so we look at the momentum of the blue car, the momentum of the orange car, and then then we look at their momentum afterwards, and since they have the same mass, we can add those two masses together to come up with 2m, and there's their velocity afterwards. So as a result, the momentum must be moving. If they're both the same mass and they collide together, then the velocity after has to be half of the original velocity of the one car. So it ends up being 2 meters per second, and it's in the same direction as the velocity before the collision. Here's another look at it. Here's the difference between the two. Here's an elastic collision, and you see there's a little spring there. And when two objects moving at each other from opposite directions, same speed, and they just transfer the momentum to each other. Here and then over here within elastic, you have two objects hitting each other and sticking together, and the momentums then are shared between the two of them. So you may have, now this is all looking at forces before the collision. After the collision, then you might have things that will change the effects after the collision, such as friction between the table and the air of a billiard table. The trucks may skid along the pavement. You'll have some friction there, and that will decrease the momentum. But in space, actually, that's kind of a great place to look at momentum, because there's no air resistance. The only thing you have to worry about is gravity. When you're pretty far away from the Earth, then gravity no longer really is of a concern. This is a picture of the Apollo-Soyuz spacecraft. This is the American Apollo craft, and this was the Soviet Soyuz craft, and they actually docked in space back in the 70s. So you can imagine there are not many perfectly elastic collisions in this world. Friction always seems to come into place, whether it's air friction or friction like tires on the road. And a ball, another example is the heat generated. If you drop a ball on the floor and you put a thermometer to it, it is going to warm up a little bit, and the floor is going to warm up a little bit. But at a microscopic level, you can have some perfectly elastic collisions, because the particles don't touch each other. They don't physically actually touch each other. They will bounce off each other because they're electrically charged, so they don't actually ever touch each other. An air track is a great way of demonstrating this, because it gets rid of the friction between the objects and the ground, so you can actually look at the conservation of momentum really well, because the objects colliding are actually on frictionless air. So one glider is loaded, so it has 3 times the mass of another glider. The loaded glider is initially at rest. The unloaded glider collides with the loaded glider, and the two gliders stick together. Describe the motions of the gliders after the collision. Well, first of all, what kind of collision is this? They stick together. It's an inelastic collision. And if the one's at rest and they stick together, they're going to go in the direction of the glider that was moving. So let's see. The mass of the stuck together gliders is now 4 times that of the unloaded glider. The unloaded glider had mass of 1, so to speak. The loaded glider had a mass of 3. The velocity of the two stuck together gliders is going to be 1/4 of the original velocity of the unloaded glider, because now the mass is 4 times what it was before. And like I said, the velocity is going to be in the same direction as before, since the direction as well as the amount of momentum is going to be conserved.